So, hello everyone. In this special for this year GAN seminar, because we have Asimina Hamakiotes, who's going to give one single talk about elliptic curves with complex multiplication and abelian division fields. So, Asimina, you can start.
Great. Thank you so much for having me. I'll be talking about some work that's joint with my advisor, Oliver Lozano-Robledo, as well as some work that I've continued to do independently. So first, I'll start with a general question. Let's let f be a number field and E over f an elliptic curve, and n some integer greater than or equal to 2. When is the division field f adjoin the n torsion abelian over f? That's one question. And if this extension is not abelian, then what is the maximal extension contained in here? And so I guess I should say that abelian division fields of elliptic curves over Q have other applications in things like the classification of torsion subgroups of elliptic curves over maybe quadratic fields, the classification of isogeny torsion graphs, Galois representations, and things like this. So first I'll go over some background. So an elliptic curve defined over a field K not of characteristic 2 or 3 is an equation of the following form, where there's this condition for smoothness. I guess more precisely, it's a smooth projective curve of genus 1 with at least one K rational point. And so here on the right, hopefully you can see the colors. There's this blue line, which is the elliptic curve itself. And there's an abelian group law on the L rational points of E. So these are the points on E whose coordinates lie in of any field L that contains K. And then we also add this point at infinity so we can get a true group law. So if you take 2 points on the curve and you draw a line through those 2 points, it'll intersect the curve at a third point. If you reflect that over the x-axis, then you get the sum of the 2 points. And so this is kind of how you can add points on this curve. And so we call the group of L rational points of E the Mordell-Weil group of E over L. So let's take a look at this curve. And throughout this talk, whenever you see parentheses next to the elliptic curve, that's just the LMFDB label if anyone wants to search the curve up. So here for this curve, we see that the Mordell-Weil group over Q is generated by the point 720, which has order 4. So this is isomorphic to Z mod 4Z. Now, if we consider the same elliptic curve over Q adjoin I, we see that the Mordell-Weil group changes a bit. Now, it's generated by 2 different points, and it's isomorphic to a Z mod 4 cross Z mod 4. So in 1928, Mordell-Weil stated the following theorem. They stated it for all abelian varieties, but for the purpose of this talk, I'll only be talking about elliptic curves, so I only stated it for elliptic curves. But if we take a number field f and E over f an elliptic curve, then the Mordell-Weil group of E over f is a finitely generated abelian group. And in particular, it's isomorphic to some torsion part and some free part. And so this E of f tors, this is a finite subgroup. This is all the points of finite order on the curve. And then we have this, these copies of Z, which I'm not really going to talk about at all today. And this R is called the rank. And these are the points of infinite orders. So we can look at a few examples of some Mordell-Weil groups. So for the first curve, y squared equals x cubed plus 1, this curve has 6 rational torsion points. So the Mordell-Weil group just has a torsion part. It's just isomorphic to Z mod 6Z. If we look at the curve y squared equals x cubed minus 2, this does not have any rational torsion points other than the point at infinity, but there's a point of infinite order. So the Mordell-Weil group is just generated by that point of infinite order, so it's just one copy of Z. Then our last curve, y squared equals x cubed minus 1,156x, has both torsion and infinite points. And you can see the torsion part here is the Z mod 2 cross Z mod 2. And then we have the free part is generated by 2 points of infinite order. So we have a Z2. And these points here are the points that generate the torsion subgroup. And then the last 2 points generate the free part. So we're going to talk a little bit about the torsion subgroup. So E bracket n, this is just going to denote the n torsion subgroup of E of f bar. F bar is the algebraic closure of f. So this is all the points in E of F bar such that the points have order dividing n. So these are finite order points. So one can show that over the algebraic closure of F, the n torsion of subgroup of E is isomorphic to two copies of Z mod NZ. And in particular, for the whole torsion, there's some integers a and b greater than or equal to 1, such that E of F tors is isomorphic to Z mod A cross Z mod A B Z. And so throughout this talk, we'll be interested in the nth division field of E over F. And so all that is you're joining the x and y coordinates of the n torsion points to a field F. Okay. So let's consider let's let zeta n be a primitive nth root of unity, and let's consider this extension, the cyclotomic field over Q. So we can obtain the cyclotomic field by adjoining the n torsion points of Q bar star to Q, right? Because essentially roots of unity, they're just torsion points, right? So we know that the Galois group of the cyclotomic field over Q is abelian, and we know exactly what it is. It's isomorphic to Z mod NZ star. Now, what if we did something similar, but instead of adjoining, the n torsion points of Q bar star to Q, we adjoin, torsion points of an elliptic curve. So we're going to let E be an elliptic curve defined over Q, and we're going to consider this, we call this the nth division field again over Q. And again, we're just adjoining the x and y coordinates of the n torsion points to Q. And for similar reasons, this is also Galois. And so a natural question to ask is, well, what is this Galois group? And so the way we can study what this Galois group is through Galois representations. So we're going to let rho En be the following Galois representation attached to E. And so throughout the talk, I'll be using GEN to denote the Galois group of the division field over Q, which is isomorphic to the image of this Galois representation. And so as we can see, in general, this Galois group is going to be contained in GL2 Z mod NZ. But in many cases, it's actually isomorphic to GL2 Z mod NZ. So a question that we're interested in is can this group be abelian? And how do we study that? Well, we can study that by looking at the image of the Galois representation, which is going to be some matrix group, and seeing, is this group abelian? I guess I should also say that I'm studying this for elliptic curves with complex multiplication, and that's because Oliver Lozano-Robledo has a full classification of Galois representations attached to elliptic curves with CM. If we don't quite have the same thing for non-CM elliptic curves, so and this question is not answered in general for a number field. So a good first place to start is with the complex multiplication, which now I will define.
Yes, I mean, could I ask something? So can you go back? So I know when n is a prime, we do know all the subgroups of GL2 Z, Fn. So that right? Don't we know? I mean, okay, my actual question is, do we know the abelian subgroup of GL2 Z mod NZ in general? Is there any characterization in the literature?
For the CM case, we know everything. For the non-CM case, I'm not as sure.
No, I'm talking in general from the group theoretic point of view. We know
Oh,
the subgroup of GL2 Z mod NZ.
yeah, you know that it can be like a Borel or
Yeah,
part.
yes, things like that.
Yeah.
Ah, we do have a okay. Thank you.
So, right. So we're studying this for elliptic curves with CM. So we say that our curve E has complex multiplication if the endomorphisms of E strictly contain Z. And this makes sense because if you think about it, every elliptic curve has the multiplication by M homomorphism or endomorphism, right? And that's just where M is any integer. So we have that it's always isomorphic to Z, but sometimes our elliptic curves have a little bit more endomorphisms. And so if E over F has CM, then the endomorphism ring is isomorphic to an order in an imaginary quadratic field K with index F in the maximal order, and we call this F the conductor. So here's an example. this curve y squared equals x cubed plus x has this endomorphism where phi of xy equals minus x of iy. And you can see that for xy on E, if you plug these into the equation, we have that minus x iy is also on E, and you can check that this is endomorphism. And in this case, the endomorphism ring is isomorphic to Z bracket I, which is the maximal order of Q adjoint I. Okay, so what has been done? So previously, Halberstadt, Morel and Stein, and Rebolledo show that if P is prime and F of the P torsion equals Q of zeta P, then P is 2, 3, 5, or it's greater than 1,000. When F is Q, Palladino gives a classification as a two-parameter family of all elliptic curves E over Q, where the third division field equals the third cyclotomic field. So Lozano Robledo and Gonzalez Jimenez study this for just elliptic curves over Q, and the nth division field equals the nth cyclotomic field only for n equals 2, 3, 4, or 5. And more generally, we have that this extension is if this extension is abelian, then n is 2, 3, 4, 5, 6, or 8. Now, they also study this for elliptic curves with complex multiplication, and it turns out that the division field equals the cyclotomic field only for n is 2 or 3. And if this extension is abelian, then n is 2, 3, or 4. And so now the next question is, if we have an elliptic curve defined over a number field, can this be abelian? So first I'll set up some notation that we have already seen a little bit of. K is an imaginary quadratic field. Delta K is the discriminant of the ring of integers. OKF is going to be the order of conductor F in K with discriminant delta KF squared. JKF is a J invariant associated to the order. So if you think of this as C mod the order, the lattice, this is just one of the J invariants. So E over Q adjoin JKF is an elliptic curve with CM by the order OKF, and a minimal field of definition for E is Q adjoin that J invariant. And so the reason we're studying this over the minimal field of definition is because you can always make that field big enough that this extension becomes abelian. So we're just interested in what happens over the minimal field of definition. So here's just an example of what I mean by the minimal field of definition. So let's take this curve E over Q adjoin the square root of 2, which is given by this lovely curve. So this has CM by OK4, which is Z bracket 4i. In this case, K is also Q adjoin I. And so the J invariant here is this number that has a square root of 2 in it. So really when we're doing Q adjoin JK4, we're really just adjoining a square root of 2. So this is the minimal field of definition. This is all we mean by that. So this is our main results summarized, right? So let's take an elliptic curve over Q adjoin JKF. This is an elliptic curve with CM by OKF and n greater than or equal to 2. We're going to define GEN to be the Galois group of the n division field of E. If GEN is abelian, then n must be 2, 3, or 4. And if it is abelian, then it's going to be isomorphic to Z mod 2Z to the K, where K ranges between 0 and 3. And so this statement is all in terms of n, but when I'm studying this or talking about parts of the result, we'll talk about it in terms of primes. So if you take the prime decomposition of n, so let's say this is the decomposition where the pi, these are all the distinct primes, we can study when GEN is abelian by studying when GEPI is abelian, because this will be the compositum of all these groups. And so if we have n be, or no, let's say 6, if it's not abelian for 2, then it's not going to be abelian for 6. So our first result is for n equals 2. Basically what we've done is we know that this can be abelian for 2, 3, and 4, but it's not always abelian for 2, 3, and 4. There's specific cases, and so that's what we've broken down. So if n equals 2, then GE2 is abelian if and only if one of the following holds. So if the J invariant is not 0 or 1728, and we have that either delta KF squared is 0 mod 4, or delta K is 1 mod 8 and F is odd, then GE2 is isomorphic to Z mod 2Z. If J is 1728, we always have that it's abelian, but in this case, it's more of a matter of, what's the group going to be. So if D is a square, then GE2 is trivial. If D is not a square, then it's Z mod 2Z. And lastly, if J equals 0, so if we have the model y squared equals x cubed plus d with d a cube, then GE2 is Z mod 2Z. So perhaps examples of cases B and C are not as interesting because we're only looking at two torsions, so you can kind of factor these curves and figure it out. But let's see an example of applying the first part. So this is the same curve we saw before. E has Cm by Z bracket 4i. This is the J invariant. So delta kf squared in this case is minus 4 times 4 squared. This is 0 mod 4. So this GE2 for this is Z mod 2Z. And we can check that this group is generated by a non-trivial point of order 2 defined over Q adjoining the square root of 2, namely this point. If n equals 3, then GE3 is abelian if and only if the J invariant is 0 and E over Q is given by the model y squared equals x cubed plus d, such that 4d is a cube in Z. And then if d and minus 3d are not squares, then GE3 is Z mod 2Z squared. If d or minus 3d is a square, then it's Z mod 2Z. So I just have two little examples. The curve y squared equals x cubed plus 2. This has j 0 and d is 2. So 4d is a cube, but d and minus 3d are not cubes. So this is what the image turns out to be. For y squared equals x cubed plus 16, this is also a j0 curve. D is 16. 4d is a cube, but and then in this case, d is a square. So GE3 is Z mod 2Z. And then lastly, if n equals 4, then GE4 is abelian if and only if J is 1728, and E over Q is y squared equals x cubed plus dx, with D being either plus or minus 1 plus or minus 4, in which case GE4 is Z mod 2Z squared, or if D is plus or minus a square-free integer squared, where the square-free integer is not plus or minus 1 or plus or minus 2, then we get that GE4 is Z mod 2Z cubed. And so here y squared equals x cubed minus 4x. This is a J1728 curve. D is minus 4, so we're in the first case. GE4 is Z mod 2Z squared. And in the second case, y squared equals x cubed plus 9x. Here D is 3 squared, where 3 is not plus or minus 1 or 2. And so we have that GE4 is Z mod 2Z cubed. So a natural question to ask is, well, how do we study this? How did we figure all that out? And this comes back to Galois representation. So this is the same definition I showed earlier. And so this is just the definition of a Galois representation for any elliptic curve. There's nothing special about it. But for an elliptic curve with CM, we know an even smaller subgroup of GL2 Z mod NZ that it's contained in. And this subgroup's almost abelian. So I'll go over that now. So first, we'll define the Cartan subgroup of GL2 Z mod NZ. So it's going to be the group generated by these matrices, A plus B phi, B delta B A, where A and B are in Z mod NZ, and the determinant is a unit mod N. And delta and phi are defined as follows. So if delta kf squared is 0 mod 4 or n is odd, then little delta is this and phi is 0. If delta kf squared is 1 mod 4 and n is even, then we have these definitions for delta and phi. And so I guess don't worry about these definitions too much. They help determine what the group structure is going to be, that's all. And so now that we've defined the Cartan subgroup, we can define this other subgroup, which we call the normalizer of Cartan, which is a subgroup of GL2 Z mod NZ, and we define it by the Cartan matrices and this complex conjugation matrix minus 1, 0, phi 1. And so I should say that this is not actually the normalizer. In the case that n is prime, it is, but in the case where n is composite, it doesn't necessarily need to be the true normalizer of the Cartan. So I'll point out a few things here that I'll say on the next slide, but I think it's more useful to say them when you're looking at this slide. So note that this matrix here, the -1, 0, phi 1, this is a matrix of order 2. So the Cartan subgroup ends up being an index 2 subgroup of the normalizer. And now looking at the Cartan subgroup, you can think of OKF as a free rank 2 Z module. And so in that case, you would have, Z plus Z, maybe square root of delta in this case, where delta is depending on whether this discriminant is 0 or 1 mod 4, right? We have one of these. And then if you mod out by n, and you take that basis, and you look at the multiplication by M matrix with that basis, you end up getting a matrix like this where all the determinants are units. So I guess all I'm trying to foreshadow is that the Cartan subgroup is going to be isomorphic to OKF mod N OKF star, so that unit group. Great. So again, let's define the scalar representation. So there's a Z mod NZ basis of the N torsion such that the image of rho En is contained in the normalizer. So that's all that we just said, that we know that for elliptic curves with CM, those Galois groups are contained in the normalizer. So the Cartan subgroup is isomorphic to this unit group, and it's an index 2 subgroup of the normalizer. And then the last thing that will come up at the end is that we actually know what the index of this image is in the normalizer. So it's going to be a divisor of 4 or 6, but if J is not 0, 17, 28, then the index of the image is just a divisor of 2. So this 2, 4, and 6 comes from the size of the unit groups in each case, right? So if you have like Z bracket I something, these are the units, and then root -3, you have 6. Right. So here's just a sketch of the proof. So for an elliptic curve over Q adjoint JKF with CM by some arbitrary order, Lozano-Robledo has explicitly described what subgroups of GL2 Z mod P to the N can occur as images up to conjugation. And so we know what subgroups are going to be possible images, and we can come up with conditions that help characterize when a subgroup of the normalizer is going to be abelian. For example, the Cartan subgroup is always abelian. Then we can apply these conditions to all of the possible images for GEP, where P is the primes that divide N, and analyze under what circumstances we get that GEN is abelian. So I realize this might be kind of vague, so I have an example of a condition, and we can check that an image is abelian or not. So first, I'll just define some notation. So C1 is going to be this matrix, which you might realize from the definition of the normalizer, the -1, 0, phi 1. And then if phi equals 0, we define C epsilon, where epsilon is plus or minus 1. And this is just, minus epsilon, 0, 0, epsilon. And then the last matrix is just some arbitrary Cartan matrix that has this form. If we let n be greater than or equal to 2, and we have some subgroup of the normalizer, if the subgroup contains, one of these matrices, let's say C1 and a Cartan matrix, then, and if these two matrices commute, then we get the condition that B phi must be congruent to 0 mod n, and 2b must be congruent to 0 mod n. And then the last line is just saying if we take C epsilon instead of C1, we get the same conditions. So we know this just says that if these two matrices commute, then these conditions must hold. So now this corollary here is saying that, again, let's say n is greater than 2 and G is a subgroup of the normalizer. If C1 is in G and we have this some Cartan matrix in G such that B is a unit, then G is not abelian. Automatically, we can say that the whole group is not abelian. And that's because if we have, let's say, C1 and some Cartan matrix commute, then by the result I just showed, we must have that B phi is 0 mod n and 2b is 0 mod n. But if n is greater than 0 and b is a unit, then 2b being 0 mod n implies that 2 is 0 mod n where n is greater than 2. And that's not true. So we get that G's cannot be abelian. So now, since Lozano-Robledo has this classification of all the Galois representations attached to elliptic curves, we can go, there's many, many possible images, but we can go through each one and kind of, use this condition to see if we find one Cartan matrix where, B is a unit, then automatically we can deduce that that group is not going to be abelian. And so here is one possible image. So if we let P be an odd prime dividing F delta K and JKF not 0 or 1728, you can either have that the image is the full normalizer, but we know that the full normalizer is not abelian, so we don't need to check that. Or we can get this possible image where this is the C epsilon that we looked at, and now here we have some Cartan matrix where phi is 0, and we have this conditions on A and B. So you can see that the matrix 1, 1, delta 1 is in here, and we also have C epsilon in here. And in this case, B is a unit, so we can just deduce that this group is not abelian. GEP is not abelian, so GEP to the n is not going to be abelian. So we've seen that this extension is mostly non-abelian, right? F adjoin the n torsion of V over F. If it's abelian, n can only be 2, 3, or 4, so it's mostly not abelian. So for this curve, y squared equals x cubed minus 2x, this has J1728. We can look at the 5 division field over Q. We get that GE5 is isomorphic to the semi-direct product. In particular, we have that this group is equal to these three, the group generated by these three matrices, and we can even check using our condition, right, that here we have C epsilon, and here we have something where 3 is a unit mod 5, so we can check it's not abelian. And another example that I included just to show you that just because n is 4 doesn't mean the group needs to be abelian. In this case, the 4 division field over Q, the Galois group of that is isomorphic to D4, which is not abelian. So what is the maximal abelian extension contained in here? Okay, so we already know a few abelian extensions contained in here. First, by the existence of the Weil pairing, we know that the F adjoin the roots of unity will be contained in F adjoin the n division field. Now for n greater than 3, if we have an elliptic curve that has Cm by an order in K, then K is also contained in the division field. And now let's say n is greater than 2, alpha is in F, and E alpha is the quadratic twist of E by alpha. Then we have that F adjoin the n torsion of E alpha is contained in F adjoin the square root of alpha and the n torsion of E. So if the square root of alpha is in this division field, then the division field for E alpha is contained in the division field for just E. If the square root of alpha is not in the division field, then we have that the division field of E alpha is equal to F adjoin the square root of alpha and the n torsion of E. And we get that this G E alpha n is conjugate to this subgroup. So basically we have that either K adjoin the J invariant and the zeta n is an abelian extension, or K adjoin J, zeta n, and the square root of alpha is an abelian extension contained in there. And again, this depends on whether or not E is a quadratic twist of a curve by alpha. And so that's great, but we don't really know if either of these extensions are maximal. So let's let Gn is the same as before, and we're going to let Ge prime En denote the commutator subgroup of Gen. So now I have the following diagram. So can you see my mouse? It's okay. The Q adjoin JKF all the way up to Q adjoin JKF En. This is the extension we've been looking at, Gen. And so now we're just building some abelian extensions, right? If we go up to K adjoin the J, this is abelian. If we're adjoining the roots of unity, it's also abelian. This is going to be abelian. We're just going up by K. And so this extension here, where we're going from K adjoin J, KF, zeta n to what should be the maximal abelian subgroup, this extension is either going to be trivial or a quadratic extension. And that's what we're going to show. And then this here is the commutator subgroup. So one way we can find what the maximal abelian extension is just start off by finding what an abelian extension is and seeing what the degree of that over Q adjoin J is. That will give you an upper bound for the commutator subgroup. Then there are other ways you can find a lower bound for the commutator subgroup, and eventually, ideally those meet, and then you know what your maximal abelian subgroup is. So I'll outline that, I think. Oh, yeah, I do here. So we have explicit matrix groups for these images, so we can compute explicit commutator subgroups. And so these are the two possible abelian extensions we talked about. We can use the degree over Q adjoin J to find an upper bound for the size of the commutator subgroup. Now this reduction map, just going from one level to one level down to the commutator subgroup, is surjective and will help give us a lower bound for the size of the commutator subgroup because we know it's shrinking by a certain amount. It turns out that this upper bound and lower bound meet for the cases that I've looked at. So it must be the case that the abelian extension we started off with is actually the maximal abelian extension contained in our extension. So here's some examples of that, or I guess results of that. If we let E over Q be an elliptic curve with Cm and J is 0 in this case, for n greater than or equal to 2. Here we're looking at P is 3, right? So earlier I had mentioned we know what the index of the image is in the normalizer. In this case, because we're Q adjoin square root of -3, we can have 1, 2, 3, or 6. If we have that the image is the full normalizer, the commutator subgroup has size 3 to the n, and we get that Q adjoin the roots of unity and square root of alpha is the maximal abelian extension. If it's 2, we also get 3 to the n, but we get a Q adjoin just the square roots of unity. And then similarly for 3 and 6, the commutator subgroups have the same size, but the maximal abelian extensions are different. Here, alpha is a square-free integer that's not -3, and this is the size of the normalizer. In case anybody wanted to actually do some of this math themselves, you can check. Like if the image has index 1 in the normalizer, then that means the image has this size. If the commutator subgroup has size 3 to the n, you can divide that by 3 to the n and check that you actually get the size of this extension over Q. So the reason you're not seeing any k's here is because k is just contained in Q adjoin the roots of unity. So that doesn't come up, but you could write this, I guess, as k adjoin those things. I mean, the Galois groups aren't too interesting. They're exactly what you would expect, but I will explain what's going on. Like, why do some of these have a square root of alpha and why do some of these not have a square root of alpha? So let's take a look at the curve y squared equals x cubed minus 6. So this has J0, and the image is this subgroup of GL2 z mod 3 to the nz, and it's an index 3 subgroup of the normalizer. So note that this curve E is a quadratic twist of the curve E prime, which is y squared plus x equals x cubed minus 1 by 8. So the maximal abelian extension is going to be, the roots of unity, well, k, which is already contained in the roots of unity, and then the square root of alpha, which is what we're twisting by, in this case, square root of 8, so the square root of 2. And so we can now look at the minimal quadratic twist E, which has this image, which is an index 6 subgroup of the normalizer. And this is a minimal quadratic twist, so we don't really have a square root of alpha to adjoin to it. So the maximal extension in this case is just Q adjoin the roots of unity. So when you see that some cases have a square root of alpha, that just means that those images correspond to elliptic curves that are quadratic twists of other curves. So now we can look at E over Q and J 1728. So this is a bit interesting because now if you see what the maximal abelian extensions are, we're looking at the image mod 2 to the n, but we're getting the roots of unity z to 2 to the n plus 1. And so what's happening here is that the roots of unity are actually a bit ahead of their time. And I think this was first noticed by Harris Daniel and Oliver Lozano Robledo. And I think It was Nathan Jones who proved that if you have an elliptic curve over Q with CM and delta KF squared is even, then Q adjoin zeta 2 to the n plus 1 is actually contained in Q adjoin the 2 to the n torsion. And so that's why we're getting some extra roots of unity. But in any case, alpha is a square free integer that's not -1. And again, k is q join I in this case, which is contained in the roots of unity. So you're not really seeing a k here, but we have that. If the index is 4, we just get the roots of unity. And if it's 1 or 2, we also get a square root of alpha. Again, the Galois groups aren't, they're just what we expect. So here's another example. If we look at the curve y cubed minus 9x with j 1728, we have that this matrix group is the image, and this is an index 2 subgroup of the normalizer. But here E is a quadratic twist of the curve E prime, which is y squared equals x cubed minus x, and it's a quadratic twist by 12. So the maximal abelian extension will have a square root of 12. And now if we look at the minimal quadratic twist, it's an index 4 subgroup of the normalizer, and the maximal abelian extension is just q join the roots of unity. Lastly, for j equals 0 and p2, we get that the size of the normalizer is a bit different. So we have j0, so we have cm by the field q adjoin square root of -3, and this time that's not contained in the roots of unity, so we don't actually get, we actually get to see k here, and in this case delta kf squared is not even, it's just -3, so we don't get that the roots of unity are ahead of their time. We just get zeta 2 to the n, and in this case we don't have any twists. So I've shown these results for p equals 3 and j0, for p equals 2, j0 and 1728. I've recently, I also just finished proving this for p equals 2, j not 0 or 1728, and you don't get anything different than what you've seen. All the maximal abelian extensions are of the same vein, where it's either just a, k adjoins some square roots and the square root of alpha, or k just adjoin the square roots, or q, and so on. And so the next step would be to study this for other primes, which I'm doing now. But the first result is just for an elliptic curve over Q with a prime greater than 2. So Daniels and Lozano-Robledo have shown that in this case, just for P, the maximal abelian extension is Q adjoin zeta P and a square root of D for some integer D. And these are the possible Galois groups. And so they just do this for one prime. They don't do it for the whole prime tower, and this is only for over Q. So my goal is to do this for the whole prime tower and also over number fields. So I have the following conjecture, that we let E be an elliptic curve over Q adjoin JKF with CM by order OKF. And if we take a prime greater than 2 or greater than 3, but it really, I think greater than 2 is fine as well, and n is some positive integer, then the maximal abelian extension is either going to be this k join jkf and zeta p to the n, or that with a square root of alpha. Alpha is going to be in q join jkf, and it'll be square free, such that the square root of alpha is not in k, which is pretty much what I mean by square free. And yeah, it will be one of these two. I think that's all I had.
Okay, let's thank Asimina for the very nice talk. Okay. Go. So let me stop recording.